Hey students, well, welcome to our effort to continue class as best we can. Um, all I can say about this stuff is that, 30 years from now, you all will all be sitting around griping about the younger generation and how they don't know how good they have it. They don't remember the great coronavirus of 2020. They don't blah, 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 blah. If any of you all are old enough to, have relatives old enough to have remembered the Depression or the Second World War, those folks tend to have a bit of an attitude. No, not a bad one, but my grandmother always sort of felt that everybody younger than her really just didn't know what being tough was. And so anyhow, that will be you. That will be you in 30 years. So, all right. So let's get on to people's questions. I'll handle a group of them as best I can. I'm going to try to keep this under half an hour, 45 minutes max. I wouldn't want to listen to me for half an hour, so I feel bad for you, but this is what we have to do. Okay, so questions that people asked. First of all, how did people know that light was a wave? Okay, so a couple people asked questions along this line. The answer to that is that light does weird things that can't be explained any other way. The place where you see this most easily is if you're in a parking lot and you see where cars leak some oil on the ground when it's rained, and you'll see like this shimmery rainbow of color. Well, the water doesn't have rainbow color. And oil, if you pour oil into a glass, even clean oil doesn't have color. It's brown looking. Dirty oil is black looking. So how do you get rainbow of color out of oil on water? And the answer to that is that light's a wave. Waves will do things like build each other up and cancel each other out in a way that like particles can't. So people have thought that maybe light was particles that shot out of a light source and then hit something and reflected into your eye. But you can't explain that rainbowy color with particles. And so you can't explain it with waves. And so those sorts of things are what got people to first begin understanding that light is a wave. All right. A couple of different questions about the Milky Way, the white path, the galaxy. Okay. So galaxy, important thing to remember. What does galaxy mean? Galaxy think of lactose. Oops, I just realized I have this flipped on reverse. Well, I'll work on that on another video. Galaxy is, sorry, that amuses me. Galaxy, that term, think of lactose, lactation, things like that. Lact involves from the Greek word for milk. Galaxy just means the white path, the milky path, okay? And so in the sky, there is this white path through the constellations. I know that showing a projection on a computer video is not the greatest thing in the world, but I'm not the most technologically sophisticated person. But I've tried to turn up the brightness so that you can see it as it goes up like this. All right. Now, to see the white path, you have to be out in the dark, really dark, out in the country. If you've been out in the country, you might have seen the white path, the Milky Way, the galaxy, because remember, galaxy means Milky Way. It's the white path in the sky. Herschel, we've learned about, had investigated this area and found that it had lots of stars. Well, Galileo discovered this first. So the astronomers came to understand that the white path was a conglomeration of stars. And then Herschel, of course, figured that if you saw more stars, that meant that things went out deeper in that direction, that the stars went out farther. Okay, but before you really get to Henrietta Leavitt, no one has any idea and where we are in these stars, how far out they go, and if there's any other conglomerations of stars out there in the universe besides the one that we are in. Okay. So then, what about other galaxies? Okay, so someone asked, how do we know that the 2 million year old light from the Andromeda galaxy is 2 million years old? How old do we know that light is? Okay, well, it doesn't have an expiration date on it, so we can't, we have to make our best estimates of it by looking at the thing that the light came from. So in the case of Andromeda, Henrietta Leavitt discovers how to measure vast distances in space. Okay, parallax measurements will tell us the distance to the stars that are closest around. You know, here's the sun, and it'll get us the distance to the stars that are not that far away. But it only works out to a certain distance. If you remember where we put our finger over an object in the room, and then the further away your hand was, the lesser the effect, the closer it was to your eye, the greater the effect. Well, if your arm was long enough, eventually that effect would go away altogether. So parallax only works for stuff close by. Henrietta Leavitt figured out how to use these powerful stars called Cepheid variables in order to figure out distances. That was then used to determine, her method was then used to determine, for example, that we are not in the center of our galaxy, like Herschel and some others had first estimated. And Edwin Hubble used that method to figure out that the Andromeda thing, nebula it was called, is far enough away that it can't be within our own galaxy, our own conglomeration of stars. So it had to be its own galaxy. So you then, by using those Cepheid variables, he's able to figure out how far it is away by using the speed of light that we've learned about, you know, way back some chapters ago that we figured out that was discovered kind of accidentally. We know how fast the light moves. So we look, hey, that object's this far away, and it takes light this fast to get here. At this speed it travels here. So it's just like driving in a car. You know, if something is a city is 300 miles away, and a car can average 60 miles an hour, then 60 times 5 is 300 miles. Okay, so 60 miles an hour, 5 hours, 300 miles. So if you had a city, someone drove to Louisville from a city 300 miles away, you would say, well, when did that person leave? Left 5 hours ago. Okay, that's the same way we work out the speed of light. The age of the light from the Andromeda Galaxy. So by looking at the Andromeda Galaxy, we say, oh, that light, given how far away Andromeda is, as measured by the Cepheid variables, and the speed that the light travels at is measured by first discovered by off the moons of Jupiter by accident. We can figure out when did the light leave the galaxy of Andromeda, and that was 2 million years ago. Of course, that 2 million years means that, well, if the universe is only 6,000 years old, like Usher had said, then if the universe was only 6,000 years old, you couldn't have 2 million year old light in it. So the Andromeda Galaxy indicates that we have a universe that's at least 2 million years old. And then as we discover and measure the distances to further galaxies, we find it's older than that still. So the Andromeda Galaxy provides an estimation that the universe is at least 2 million years old, and farther away galaxies provide an estimation that it's even farther away or older than that. Right. Another question in regards to light waves. Someone asked, are shorter waves of light harder to see? In other words, is violet light harder to see than red light? And I think the answer to that is no. The length, it's just like high-pitched noises are not harder to hear. Well, I guess for someone with good hearing, they're not harder to hear than low-pitched noises. So if you hear, beep versus brr, they're both kind of the same if your hearing's good. I know that people who lose their hearing, they tend to lose the high-pitched stuff first. And I don't know if that's because in some way high pitches are harder to hear, or if that's just the way ears are. I don't know enough about physiology to answer that question. But as far as I know, short wavelength light, violet, is not harder to see in some way than long wavelength light like red. Okay, so all right. Now, what is a nebula? This is another question. What's a nebula? Is it its own material, or is it stars? And the answer to this question is, well, it depends on which kind of nebula you're talking about. Okay, so spiral nebula turned out to be stars. Okay, and other nebula turned out to be its own material. The other nebula are in our galaxy. Okay, so I'm not sure if I can pull this up from this distance, but here, let's see. In the constellation of Orion, get out of the way, there is a nebula. Now the screen's washing this out, so that looks too bright. Okay, that is a cloud of dust and gas in our own galaxy there in the constellation of Orion. Okay, that's a nebula. That's a gaseous nebula. Its spectrum is the spectrum of a non-dense material. It gives off a line spectrum. Okay. Now, in the constellation of Pegasus, well, next to the constellation of Pegasus, it's in the constellation of Andromeda right there. Okay, that thing is the Andromeda Nebula. You can see both of these nebulae with the naked eye, and that one is the a spiral nebula, which we now know to be a galaxy. All right. Then, if I look at, now this is computer simulations of this. Now I'm going to go and ask for drawings. That is a drawing of the Orion Nebula, which is its own material, gas and dust. All right. And then that is a drawing of the Andromeda. Okay. So originally, you know, the astronomers didn't know the difference between the one and the other. Except that one kind of tended to be spiral shaped, like that, okay? And then others tended to be kind of more blobby shaped, like that. And this is what they look like in the telescope. That's why I got all those pictures in the book of these things. So it depends on what kind of nebula you're talking about, whether it's its own thing. If it's a galaxy, it is, okay? If it's a cloud of dust and gas in our own galaxy, then it is not its own thing. It's part of our galaxy, if that makes sense. Now, somebody said, asked the question, why are the stars hot? So stars, we learned from their spectra, they have a rainbow spectra. It's just like the spectra of a hot, glowing piece of metal. So stars must be hot, glowing objects. And so, well, what makes them hot? For a long time, nobody had any idea what made them hot. I mean, okay, so there's maybe I shouldn't say that. There's a variety of things you could say they were hot. Well, if the universe isn't that old, they could have just been created hot. And if they're big and really massive and dense and they were created hot, it'll just take them a long time to cool down. So maybe they just haven't cooled off, right? So they're just hot because they were made hot. And then they take a long time to cool off because they're so big. The other idea came that astronomers get the idea that maybe, things formed from a collapsing blob of gas. We've talked about this, about like looking at the moons of the Jupiter and planets of the solar system and how it looks like everything sort of rotates, like it came from an original rotating thing of gas. Was the idea that the collapsing of the gas made it hot. Turns out that didn't, as we learned more about the age of the universe, that wouldn't provide an answer either. It wouldn't last long enough. And so then the next thing, but after that idea began to fall apart, it turns out that about that time we began understanding nuclear physics. And we now understand that a star its gravity is an object whose gravity is crushing it inwards and crushes the center of the materials together so hard and so hot that they fuse. They get nuclear fusion, like a hydrogen bomb is going off on the inside of the star. And a star is this balance between its gravity, squeezing it in, and the explosion of the hydrogen fusion on the inside, pushing out. That anyhow, it's that hydrogen, that nuclear reaction that makes the star stay hot. Someone asked, are the stars that we see that look brighter, are they closer than the ones that are dimmer? And the answer, that's what we found is no. Okay, that through parallax measurements, we see that some bright stars are actually pretty far away. Deneb is one of them. You can see Deneb easily with your naked eye, and it turns out it's really, it's like pushing 3,000 light years away. And whereas like Sirius looks bright and it's only 8 light years away. Okay. So, and there's some stars we see that are dim that are actually pretty close. Okay. Why? Because they're just wimpy stars. So no, that's one of the things we learned is that stars come in a great variety of power outputs. And so there's some dim bulbs that we see up there in the sky that they look dim because they're just really far away. But some of them look dim because they're close by and they're just dim. And we have learned that there are oodles and oodles of stars that are so dim we can't see them. Only since telescopes have gotten better have these stars been visible, because they are because they're so dim. They're called red dwarfs. And we think, in fact, that that's what most of the stars in the sky are. We just can't see them. That there's oodles and oodles of these red dwarfs.